I'm going to do a little bit here on linear expansion. This is a maths lesson. But in the maths lesson, what I'm going to do is I'm going to try and explain a little bit of the practicality behind the maths. Because when I was started off, when I was an apprentice, I used to hate maths, and because I didn't understand how it was relevant to my trade. But this time I'd like to try and make this relevant, show you why we even bother getting involved in this sort of stuff. So the theory behind it, and then just the simple maths. Now, if you're sitting down there and you're thinking, I hate maths, just let me reassure you that all you have to do in this question is multiply three things by one another. When you see this question on Theory 3 paper, it's one of the 18 questions you're going to do on Theory 3, you're just going to remember, oh, this is really simple. Don't mind all the technical words, because in the end it boils down to multiplying three things by one another. Now, you've just looked at a video, and on the video you've seen a copper pipe being heated, and you've seen a dial. Let me explain to you what's happening here and what we're trying to prove by this little experiment here. What we're trying to prove with this experiment is that when you heat a piece of metal, you get what you call you get expansion anyway. It's going to swell up on its width and on its length. But we don't care about the width in this case. We only care about the length, how long it gets when it's heated. Because this is relevant to you as a plumber, because when the pipe gets hot, it's going to expand. Now, if you think of circumstances where the pipe might expand, where it might cause problems, therefore it has to be taken into consideration. Now, explaining the video there, this is a dial here, a little gauge, that indicates when it starts to move around like this in the clockwise motion. What it's doing is it's indicating that the pipe is actually stretching. It's putting pressure against this point here. The pressure then makes the dial move. So in the experiment, what's happening is, as you heat the pipe, it's proving that the pipe is actually expanding on its length, which is linear expansion. So when people design pipe works, if you go out and look in the workshop, overhead in the workshop where you are at the moment, what you're going to see is, you're going to see a long run of pipes, and every so often there's a turn at 90 degrees, there's a little shape that's like this. We just look at the pipe runs along, and it comes up like that, then it comes this way, then it comes down, and then it keeps going down like that. Now that's an expansion joint. As the pipe swells on the length, it has to have, if it's fixed rigid and it hasn't got these expansion joints here, it will burst and buckle and break. So it has to have these, and these must be allowed. Now, there's other ways around this. If you just look down here, you've got this type of a joint here. You can see this is like a Malone. It allows for movement in and out like that. And this is to make up for that same factor. The factor that when the pipe is on a long run and you're getting this movement because of heat, that it allows that in and out movement. And that's another way of getting around that, separate than the way up there. So, when an engineer is designing a pipe run for you to install, he has to allow for this movement. So that's the theory around it, and he has to calculate for that. He has to say to himself, oh, I wonder how much this pipe is going to expand. And it expands due to heat. And the heat makes the pipe, as I say, get longer on its length. So there must be some way of calculating that, and there is. And this is the way to calculate it. Right. On the 18 questions you will get on Module 3, this is how the question will look to you. Now, never mind all these scribbles around the numbers here. They're only something I'm going to indicate now in a minute. But the example of a question will be something like this. And believe me, I don't want you to be frightened by this, because just because the words might seem a little bit heavy or technical like this as we go along, to some of you, it depends on where you're coming from at this stage. But in the end, just remember, keep it simple. It's going to be about multiplying three things by one another. So when you see the question, just be reassured, oh, this is the one where that guy on the tape said, multiply three things by one another, and that's the answer. So, let's have a look. The question example would be, a copper pipe 6.5 meters in length at a temperature of 50 degrees increases its temperature by 15 degrees. Find its new length. And that's what you're asked. So the coefficient expansion rate for copper is that. It's 0.00016. Now, every time you see that question, you're going to be given these three things. You're going to be given what the original length, that's the length of the pipe. That's before it got hot, before the temperature went up. A degree of temperature, before it got hot by 1 degree, it was 6.5 meters in length. Right. So the temperature gets higher, it goes up by 1 degree, it starts to move. On the length, like the video there, like the dial was indicating that it's starting to swell in its length. So, if the temperature goes up by 15 degrees, it's going to start getting more than it is by 15 times that one. Now, because all materials are different and they all behave differently under the heat, we have to know how much per 1 degree of temperature rise does copper, lead, tin, plastic, and there's no way you could ever calculate that. That has to be calculated in a laboratory condition, and that has to be given to you in the question. And like everything else in this question, it'll be given to you. The three items in this that's going to be multiplied by one another, there they are. The original length, the temperature rise, and the coefficient for whatever material that you're using. So, let's have a look then how you put this question together. First of all, there's a formula. And the formula is just incorporating the three things. It's the original length by the temperature rise by the coefficient of linear expansion for that particular material, wherever the material is that you're going to be working. So, in the question around there, and I'll keep flicking back and forward because I'm going to show you. In the question, a copper pipe 6.5 meters long at 50 degrees increases its temperature by 15 degrees, find its new length. The coefficient and expansion rate for copper is this. Now watch. In the question, you're given the original length. In the question, you're given the temperature rise. In the question, you're given the expansion rate. Watch it again. Let's take the first one. The original length 6.5. The temperature rise given 15 degrees. The coefficient rate for the material given, and there it is there, 0.00016. So, if, like I said in the beginning, this is only about multiplying three things by one another, then it all boils down to this. The 6.5, the original length, the 15, which is the temperature rise, and the coefficient for the particular material you're asked for, in this case it's copper, it'll be given to you. Be given, be given, be given. You multiply the three by one another. Original length, temperature rise, multiplied by the coefficient of linear expansion for that particular material. When you multiply them out, that's the answer. That's how you do it. Okay, thanks.